Hello, and thank you to the IET for having me to introduce the grand finale of our brand new virtual presentation competition, Present in 10. I am Laura Gil, and I am the chair of the IET's Young Professionals Committee, in which this competition was created. Present in 10 started as a small project within our committee as we tried to create an online competition to take the place of our in-person event Present Around the World. As due to the pandemic, the lack of group gatherings and international travel hasn't permitted this to run. In Present in 10 first year of running, we saw over 200 entrants presenting their topics and networking with fellow participants. The Present in 10 competition ran 42 hits, in total over 3 rounds, to produce the finalists you will see today. They have each been selected as the best within their theme. These themes are sustainability and climate change, digital futures, and healthy lives. Xiang Hao, who is presenting from the theme Healthy Lives, is a second-year PhD candidate in the Department of Bioengineering at the Harvard University. Connor, who is presenting from the theme Digital Futures, has recently graduated from the University of Kent with a first-class honors in Electronic and Communications Engineering with a year in industry. Paul, who is presenting from the Sustainability and Climate Change theme, studied aerospace engineering at university, and for his master's group project, developed a prototype for his presentation concept, generating renewable wind energy using kites. For this grand final, we have invited 4 amazing guest judges across all theme industries. If you want to check out who they are, look on our social media accounts. Our 5th judge for the competition is you, our audience. After all presentations have been given, as the audience, you will be able to vote for your favorite. This will have a 20% influence over the final scores, so choose wisely. Information for this will follow on the screen after the last presenter. So without further ado, I'd like to introduce our first presenter in this grand final. Xianghao Zhang will be presenting a deep learning head model to rapidly estimate traumatic brain injury risks.
Hello everyone, I'm Xianghao Zhang from Department of Bioengineering at Stanford University. Today I'm going to present you a deep learning head model to rapidly estimate traumatic brain injury risks. Before I get started, may I ask, how many of you are sports fans? Thank you. And how many of you are fans of contact sports such as soccer, football, and American mixed martial arts? Boxing. Thank you very much. Well, for hardcore sports fan like me, the word traumatic brain injury has never been an abstract one, because traumatic brain injury, or TBI, has become a global health challenge. It affects more than 55 million people worldwide and causes more than 2 million emergency department visits in the US alone. It is also prevalent in our daily life, which could be caused by car crashes, military combats, various sports. It could also be caused by accidental falls and even domestic abuse. As you can see, TBI affects both the young and the elderly, both male and female. What also needs our attention is that more than 80% of the TBI are mild. Instead of directly causing death or disabilities, this kind of mild traumatic brain injury are harder to detect, but could still lead to brain damage accumulation. Because after the head got impacted, the brain strain in the head could lead to multiple pathologies that could contribute to even long-term cognitive deficit and even neurodegeneration and chronic traumatic encephalopathy. Therefore, as researchers, we are always trying to find better ways to detect TBI as early as possible to avoid brain damage accumulation. Thanks to decades of research, brain strain has been shown by researchers as an effective injury predictor, and a state-of-the-art method to calculate the brain strain is called the finite element modeling, or FEM. If we provide the FEM with the head movement kinematics, which describe the head rotation during the impact, it takes around 7 hours for the FEM to model the brain strain for one impact. How does that sound like, and what does that mean? Well, for example, if a football player got impacted in the head during play, it takes almost half a day before we could get the brain strain. And when we finally got this precious TBI risk information, I'm sorry, but the player have already been impacted for much more times. Therefore, the FEM is not applicable in real-world, real-time applications in monitoring the TBI risks. We must accelerate. Therefore, I was motivated to use a new neural network technology to develop a system that learns the mapping between the head impact kinematics and the brain strain. And here, the input and the output are the same as those for the FEM. The input are the head movement kinematics that describe the head rotation during the impact, and they could be measured by the instrumented mouse guard with these kind of sensors, wearable sensors in it, and they are also referred to as the instrumented gum shield for players of football, for example. And the output of the system is the brain strain, the same as FEM, and we also refer to it as FMPS. And now you may wonder, why could neural network do that? How could that do that? And what is deep neural network? Well, a deep neural network is a computational framework that simulates the organization of human neural network. It can model the relationship between the input and the output by processing the input data with layers of connecting weights. As you can see, the connecting weights are really the key components of the neural network, and they are learned through data. Once we could train the neural network and learn the connecting weights, and if we get a new head impact kinematic, we could process through this neural network and get the output, the brain strain predictions. In order to train the neural network, we have collected different types of head impact datasets to train the neural network. And here, firstly, we got the head model simulations by impacting the test dummy head with an impactor ER lab. We've also collected 3 on-field datasets, 2 of them from college football and 1 of them from mixed martial arts. And finally, we combined all the data to be the mixture dataset to develop the ultimate model for the users to use. With different datasets, we trained a 5-layer neural network to predict the brain strain. And now one may wonder, how well does the model perform and how accurate it is? Well, here comes the results. Firstly, we have shown the accuracy of the model in terms of the mean absolute error, the MAE, between the predicted brain strain and the reference brain strain given by finite element modeling. We could see from this figure, all the predictions or the errors are smaller than 0.035, which is much smaller than the concussion threshold, which is assumed to be 0.4. Meanwhile, on 4 out of these 5 datasets, we could see that the error get close to 0.01, which is already the accuracy for finite element modeling. With high accuracy, what is the most important advantage of the deep learning head model is that it reduces the time to compute and model the brain strain for one single impact from 7 to 8 hours to be within 1 millisecond. And this is just with a personal computer. Furthermore, we have also visualized our accuracy with 3 example impacts with different levels of severity. And here we show the high string regions given by our deep learning head model and the reference model from the finite element modeling with highlighted regions here. We could see that the high string region predicted by our deep learning head model are quite similar when compared with the reference FEM results. We have also visualized the accuracy with the three subplots on the right, with the x-axis representing the ground truth brain strain and the y-axis representing the predicted brain strain. And here, each dot in this plot shows the prediction for one brain strain for one brain element. We could see that all the predictions for all the brain elements for these three cases lie closely to the reference line, y equals x, which means the predicted brain strain are really close values. The values are really close to the reference values of brain strain modeled by finite element modeling. With a high accuracy and short computational time, this deep learning head model will really enable the athletes and medical professionals in sport teams to monitor the whole brain strain. And in this way, the players could be instructed to seek for medical inspections such as CT and MRI brain imaging and early intervention in time to prevent any further brain damage. And for researchers, this deep learning head model could also help them to shorten the time for the head impact analysis, and this could significantly boost the research efficiency as well. And meanwhile, for the developers of the protective gears in the industry field, this model could also help them to evaluate the effectiveness of the protective gears, such as the protective helmets, with the fast computation of brain strain. And if you want to know more about this project, you can also refer to our publication listed here. This is this project I have done at Stanford in my rotation, and my PhD work has been built upon that. With my effort, I hope to tell those around me who are willing to play contact sports that a world without any fear of traumatic brain injury is just on the horizon. That's all. Thanks for the privilege of your time.
Next, in our Presenting 10 final is Connor Meringolo, who will be presenting hybrid wheel-legged quadruped with posture control.
Hi, my name is Connor Meringolo, and this is my project, the Hybrid Wheel-Leg Quadruped Project. I'm a University of Kent student, and I've just recently graduated, and I'll be going into Airbus robotic systems in September, which is fantastic. But I wanted to kind of tell you and the audience what it's all about, my project. So I believe in space exploration, and I believe that every robotics project can be applied to basically any industry. Now, when I say that, I always think about the rovers on Mars, and in that sense, you have rovers that can drive, and they kind of can get stuck in ditches, and there's a lot of actually mobility issues when it comes to space exploration. However, for example, ETH Zurich in the bottom left, you have a robot that can get out of ditches, can explore in more complex environments like cave systems, and is currently being in production. And I kind of want to say that these comparisons are really important, because when you're thinking about the evolution of robotics, you always kind of picture yourself a rover, you kind of picture a humanoid robot, but in reality, you can actually mix two things together and have something even better. For example, a hybrid wheel-legged robot, which would combine both of these elements. And I kind of want you guys to think about that during this presentation. The next thing I would like to say is logistics. You have the industry of logistics, which is basically a backbone of our human existence, as in we have warehouses that deliver, like Amazon Prime, Amazon Scout. You have those things that deliver us parcels, and we don't really think anything of it anymore, which is absolutely fantastic. And you've got Handle from Boston Dynamics that can deliver so much warehouse stuff, like packages and stuff, thousands and thousands of packages a day, well, we could never do that as humans, which is absolutely crazy in my mind. And I think that you really need to kind of think about that in your brains, that a human could never do what, for example, Handle could do, where they can pick up kilos of packaging and just move it effortlessly, and you don't even need to pay them. And I think that's a very, very important thing to think about as well. The advantages of having a bipedal wheel-legged robot is that it has the speed of, for example, Scout, but it also can reach new heights, like new shelves and everything like that. And it's kind of opening new doors to what is possible. And this is where my project comes in. This is Laika, which is inspired by the first dog in space. I thought it was quite a cute name for it. And my main objective was to create a quadruped from scratch. But not only just a normal quadruped, I wanted to involve a mobile wheel system onto this quadruped to give the mobility of a quadruped that a rover would have, which would combine the complexity of the quadruped, allowing it to make movements that are impossible for other mobile robotics, but have the speed and have the ability to drive as quick as a rover or as an electric mini car, for example. This is also, when I say from scratch, I'm talking about PCBs, software, hardware. This was all done by myself. And I was very lucky to be able to make a posture control system in addition to that. I also had additional objectives. For example, I wanted navigation and planning techniques. For example, like dead reckoning was investigated, and other navigation techniques. What I wanted to show you as well is the PCB design in the top left. You have this PCB design that I believe I will be taking forward after my degree, and I would like to invest into this project myself and hopefully make a commercialized project of this one day, because I do thoroughly believe this is the future of robotics in terms of mobility. This is a little bit of the systems diagram in the bottom left as well. I just kind of wanted to show you to kind of get your heads into the right space, if you get what I mean. It also consists of accelerometers, 10 motors, and allowing to have some pixie cams and cameras to kind of record or even just scan packaging for logistic purposes. So this is actually Laika in real life. This is him standing up, and it's actually made out of PLA plastic. It only weighs 1.7 kilograms, and it has 2 degrees of freedom. Now, people are probably wondering right now, what is degrees of freedom? Now, this is basically, if you think of a graph, you have an X-plane going to the side, and then a Y-plane going up. Now, this is kind of like directions. So like 2DOF means it can go in 2 directions of like a graph. So it can go up and it can go to the side. Whereas, like, for example, a 3DOF would be a Z-plane as well. So it could go up to the side, but then it could go this way as well, forward. But however, my next design will have 8 degrees of freedom. And for example, Boston Dynamics Spot has 16 degrees of freedom. So you really increase, the more degrees of freedom you increase, the better complexity you have in your movements, which means more accurate, which is, from a business standpoint, you need a more accurate device to perform more precise actions. Now, there was a big thing with the control strategy, because all robotics needs a control strategy, especially with a quadruped, because the complexity of having it balance, having it stand up is phenomenal. You have to make sure that if you push over the robot, it's not just going to fall over. You need to have it stand back up, because if you're thinking space exploration, if a rover gets stuck in a ditch, it's game over. But with a quadruped, it can get itself out only if the control system is good. Because if the control system isn't good, it's just going to try and climb out and just fall on its back, and then you're as bad as the rover. But we are allowed to investigate further and get more complex with these robots, which means that we can have a balance system. So the posture control system, I will show you in the next slide some results, which is really lovely. But I do want to show you the next kind of navigation and path planning techniques, which is the 2 images on my left. This is called an occupancy grid and a probabilistic roadmap. I actually mapped this out of my lab in my universities, because due to COVID, I had to do everything in my dorm. So this was as accurate as I could get it. But this is basically planning the quickest possible route through one of the lanes in my lab. And I also thought this would be a very good application for logistics, because obviously you have different areas into a warehouse. And I thought it was a very nice application, and to show you guys what kind of thing, because it's not just space exploration, it's not just like the medical sector, you can go into many other sectors by just including this one robot. Now, I just wanted to show these pretty graphs to you lot, because I think that when I showed my lecturers, they were very happy. So I thought I'd make you very happy too. These graphs are basically showing that the top left is the accelerometer. So that's basically measuring the acceleration, but you can actually use that for balance. So you can say, for example, this, my hand here would be at a 0, 0, 0, which means that it's flat. Whereas if I went like this, it's off. And basically what these graphs are showing is that the motors are correcting to whatever imbalance there is, it corrects accordingly, which I find is really cool. And plus it's very pretty. This is actually it moving, and I will talk a little bit about the payload now. So the payload actually stationary, so static payload, could hold about 1.5 kilograms, which is almost its entire body weight, which I found absolutely fantastic. And in comparison to, for example, a project called Helios 1, which is one of my inspirations for this project, that was a team of 6 or 7 master engineers that could get about 5 to 10 kilograms. But I feel scaling up will lead this to be exactly like Leica, even better maybe. Because I'm only one engineer, and I hope to maybe invest into some more hardware to make this product better and maybe on the same level as some of these other projects one day. But I will say that the moving payload was only 1.2 kilograms roughly before it would break. But we did actually get it clear and no issues at about 0.75 kilograms, so 750 grams. The purpose of this design, what is it? Well, I want to push for the future, and I want to basically involve 2 types of mobility. And I basically want to increase the efficiency and, yes, increasing the complexity of the device, but increasing the complexity does improve the business side of things in terms of the precision of its tasks, and be able to reach for the stars in that way, as in we be able to apply more things to it. And I think that going into other industries is really important for robotics, because that's the next stage of evolution, in my opinion. Now, I kind of wanted to just show you before we go, thank you for listening to my project, but have a look at my 5-month plan. And I hope to see you soon, and hopefully you'll follow this kind of project later in the future. Bye-bye.
Finally, I'd like to introduce our last presenting 10 finalist, Paul Longa, who is presenting Airborne Wind Energy, Why I Love Kites and You Should Too. Remember, after this presenter has finished, we will be showing a recap of all presenters, and it will be over to you and our judges to make your winner decision.
Hi, my name is Paul Longa, and I'm here to talk about the future of wind energy. And I'm not talking about wind turbines. I'm talking about kites. Some of you may have heard about how kites can power our future, but I imagine most people haven't. In this presentation, I want to inform and persuade, so I can really answer the question of why I love kites and you should too. Around my local city, Leicester, in the United Kingdom, and in the various stages of the competition, I have asked the question, what do you think when I say kites? Here are some of the answers. For many, kites evoke a response of childhood memories, of toys, of fun. As you watch this presentation, I want you to reflect on your answer, and maybe you'll see what I see too. When I look at a kite, I see the future of wind energy. There's an incredible amount of power available in the wind, and in order to understand that, I want to take us back to wind turbines. Don't be intimidated by the equation, because it will appear a few times in this presentation. What you need to know is that the power available in wind increases proportionately with the area and with the cube of velocity. A in this equation represents the wind-swept area, which increases with the square of the length of the blades. Over time, material capabilities, growth in the green energy industry, and the passion of engineers to always push technology has caused wind turbines to explode in size. Currently, the world's longest wind turbine blade is 107 meters long. Although certainly impressive, this isn't a revolution. There are limits of material strength that clever mechanical design and material engineering cannot so easily beat. Wind turbines have also exploded in height over time. This is because at greater altitudes, we get not only stronger wind speeds, but also more consistent winds. If we were to reach high enough, this could even help us solve one of the biggest problems within green energy, the intermittency problem. The problem of which that most renewable energies aren't reliable or consistent, as shown by the peaks and troughs in this graph. As stated earlier, wind power increases with the cube of wind velocity, so there are major gains to increasing this. We can't directly control the wind speed. Instead, we look for locations and altitudes where wind speed may be greater. Looking at this wind map 100 meters above ground, where windy areas are darker red, you can see why offshore wind energy has remarkable potential and is an industry that grows year on year. The tallest wind turbine has a hub height of 178 meters, but to look at the real potential of wind, we need to reach higher altitudes. The area of dark red represents greater wind speed, and look what happens as you increase the altitude from 250 meters to 500 meters above ground, and from 500 to a whopping 5,000 meters above ground. And you can just see how intense and strong the wind is. This graph shows how quickly wind speed and power grows with higher altitude. It becomes clear why we build wind turbines to such great heights. To engineer an even taller tower capable of safely supporting a massive nacelle and rotating blades is a great engineering challenge. A challenge where we are reaching the limits. And for something at 5,000 meters, may be completely impossible with conventional methods. From what I've said, it is clear that when it comes to wind energy, bigger is better. But there are technical limits to overcome to reach new heights and areas. While I propose a solution that can reach significantly higher altitudes, sweep a greater area, and be deployed more easily in more locations, all for the fraction of the cost of a wind turbine. This solution is airborne wind energy. A growing community of those that share a vision for the future of wind energy. This is both a promise and a technical challenge to take us away from the traditional three-bladed turbine and to move us to kites, wings, and drones capable of harnessing the power of high-altitude winds in a cheaper and more flexible way. The concept is simple. The bulk of the energy of a wind turbine is generated by the outer part of the blade due to the higher tangential speed. The inner blade part, nacelle, and tower add a great and needless weight. Airborne wind energy aims to eliminate the unnecessary and leave us with the most useful parts of wind power production, known as the outer blade, airfoil, wing, or as the focus of this presentation, the kite. This is the prototype that I, in a group of 6, developed at university. The system architecture diagram shows a kite attached via a tether to the ground station. The mechanical power input is a multiplication of the traction force on the tether, which comes from the kite lift multiplied by the reel-out speed. The spooling mechanism uses electronics to control the kite in a figure-8 pattern. As the kite reels out, the drum, which is coupled with the generator, rotates, generating power. Using an onboard control system or additional tethers, the shape of the kite can be manipulated to control the coefficient of lift, CL, allowing it to be reeled down using a small fraction of the power it generates. In this prototype, on a £400 budget and limited to an altitude of 60 meters to comply with legal authorities, using a small 0.044 square meter kite and wind speed of 6 meters per second, we were able to generate 5 watts of power, enough to power a small light bulb. Although the power here isn't great, what has been displayed is the potential. Adapting the same technology using that same small kite and just going to 250 meters above London in a 60-second rise time, the kite produces enough power to charge your phone. Take the same system to an offshore location, and you can watch 6 hours of TV. If we use a larger 3-meter square kite in London, this could power 4 laptops for a day. Taken offshore or made 6 times bigger, you can power 3 average UK houses. I also have asked the question to the public, can you see any other potential uses? Here are some of the answers. Best estimates put airborne wind energy at a mass reduction of 60 to 90% compared to conventional wind turbines. This also scales well with the cost reduction at an estimate of £30 per megawatt hour for the market entry level predicted for 2030. This price will only improve as the system is scaled up to a 3/4 cost reduction over the life cycle. There are also so many other benefits that are harder to quantify, such as shipping, locations, and potential for humanitarian relief situations. Making a kite 6 times bigger or deploying the system offshore is a lot easier and cheaper than increasing the height of a wind turbine. The system that could power a house is small enough to be transported easily over land in a car or van, making this ideal for emergency disaster relief situations. As there is no need to create a deep foundation for the tower of the wind turbine, this also opens up the technology to a world of locations, including mountainous or marshland. Furthermore, the rotating components are located on the ground, making this type of system significantly easier to repair, which would help to further reduce the operating cost. Starting from the original concept proposed by Lloyd in the 1980 paper Wind Kite Power, there have been large developments made in the concept of airborne wind energy. This slide shows the most promising advancements made by 2 different companies and their technology readiness number, which at the most developed is a 6, signifying system development and technology demonstration. This graph shows the kite gem power curve, the most similar to what I have described, but uses 2 kites in a pumping motion to generate 3,000 kilowatts between 500 and 1,500 meters. The next step for airborne wind energy is a technology readiness number of 8, where the system is flight qualified, and I believe that the technology is ready. AWE is a fantastic concept and viable alternative to traditional wind turbines. In my opinion, the biggest hurdle in the future of wind energy isn't the control systems, power transmission, kite manufacture, or any other technical difficulty. The biggest challenge is informing and persuading people to get on board with the concept. I hope this presentation has done a little bit towards that, and by listening to me, you can understand why I love kites, and you should too. Thank you very much for listening to my presentation.
Hello everyone, I'm Xianghao Zhang from Department of Bioengineering at Stanford University. Today I'm going to present you a deep learning head model to rapidly estimate traumatic brain injury risks. Well, a deep neural network is a computational framework that simulates the organization of human neural network. It can model the relationship between the input and the output by processing the input data with layers of connecting weights. As you can see, the connecting weights are really the key components of the neural network, and they are learned through data.
Hi, my name is Conor Maringolo, and this is my project, the Hybrid Wheel Leg Quadruped project, because all robotics needs a control strategy, especially with a quadruped, because the complexity of having it balance, having it stand up, is phenomenal. You have to make sure that if you push over the robot, it's not just going to fall over. You need to have it stand back up, because if you're thinking space exploration, if a rover gets stuck in a ditch, it's game over. But with a quadruped, it can get itself out.
Hi, my name is Paul Longer, and I'm here to talk about the future of wind energy. And I'm not talking about wind turbines. I'm talking about kites. Making a kite 6 times bigger or deploying the system offshore is a lot easier and cheaper than increasing the height of a wind turbine. The system that could power a house is small enough to be transported easily over land in a car or van, making this ideal for emergency disaster relief situations.